amazing. You'll never be able to look at circles the same way after I show you the way to work out the radius of this circle. I've got something special for you today. I have a sequence of numbers that I want you to be able to work out what the next number in the sequence is. These are fractions, so it's going to be 1 on 15, 1 on 23, 1 on 39, 1 on 63, and then something. There are lots of ways I could show you how to solve this, but today I'm going to show you a very special way how to solve it. Okay, so we're just going to put this over here. I need to get some equipment. Okay, I've got to start drawing some circles. Oh my goodness me. Have you ever done a video where it's like the paper itself has to be precise? Now I can use my other precision instrument here, my second circle. Circle number 2. Look at that. Okay, so these ones are exactly the same, and they're half the diameter of the big circle. This is going to be fun once we actually get there. That was hard to get these ones to kiss. So they're now kissing. These are kissing circles, so mathematically we'd say that they're touching tangentially. They're kissing now. Okay. Brady, you know how hard it is to get 4 circles to kiss? Do you know how hard that is? You know, I have to confess to you, I've done this a few times. This is the best time I've done it.
That's nice.
This blue circle here just so happens that the radius of this blue circle here is 1/15 of this big circle. It's 1/15.
Hang on.
Oh. Okay, let me keep going. So this is called a Pappus chain, what I'm doing here. So having one circle touching the inside of another circle, kissing, and then having circles fitting in and touching all one another. It's a big touch fest today. So these things have been around for a long time. Okay, so this one here, touching, touching, touching. So this one here, this new blue circle, this one happens to be 1/23 of the original radius. 1/23. 1/15, 1/23. This one's good. Look at that, beautiful. But it is very zen. The next one here, this little guy, happens to be 1/39 of the original large circles. There you go. I don't know how much more of this compass I can use. Okay, so this guy here, his radius is 1/63 the original radius of the big circle. 1/63. And so what's the next one going to be? Well, let's draw it in, shall we? This here now belongs to these circles. And so the question is, what is the radius of this circle in reference to our first circle? Now there's plenty of ways we could actually work that out. We could get busy with our rulers and start drawing triangles, and maybe start getting angles, and maybe start using different kind of theorems and whatnot to try and get there. But there is one way to solve this problem, which is absolutely amazing. Absolutely amazing, Brady. It is the way to solve this problem. What I'm going to show you is actually amazingly hardcore. There's a huge amount of information dealing with this. So what you have to do is I'm going to try and show you just what we need for this problem. And hopefully you can go and have a look at all the other stuff in your own time. But this is something that we just got to, Brady, you have to trust me. I'm going to show you exactly what we need for this problem and no more. But if your imagination is fired up, that's because you're thinking. That's good. The way to solve this problem is using a method called circle inversion. As a quick introduction, I think most people have seen a reflection of themselves, correct? So if you think about that, you've got your eyeball here. So here's your eyeball. So now you know how reflections work, right? So what you see is the mirror opposite. But what actually is going on is it's this distance here, 22. We're going to do this quite rough, Brady, if that's all right. Yeah. Okay, we know how mirrors work, don't we? So look at this. It's the eyeball. It's your eyeball looking back at you, right? This is called a reflection. So we're going to do a special type of reflection to solve this problem. It's called a circle inversion. Okay? Now this is how it works. First off, you've got to start with a circle. So this circle here, it's our circle of inversion. So first of all, what we need to do is we need to know the radius. That's really important, Brady. Okay, so in this case here, the radius is 60. Say we put a point out here, okay? So say we put a point here, okay? And that point there is going to be A. And this point here is O for origin. So now, we did a reflection. What happens in inversion? First of all, we're going to measure OA. So we know OA equals 30. So this point here, we're actually going to invert it. And this is how you do it. You take this length here, right, which we know is 30, and you multiply by the point we're going to, which we don't know where it is just yet, and it equals the circle radius squared. So this equals 60 squared. So in this case, this is 30 times where we want to go equals 60 squared. So if we just divide through and do a quick little bit of calculation, and that goes twice, so that means OA equals 120. And so what we've done there is we've actually taken this point all the way out on exactly the same line to here. So this length here is OA dash, and it equals 120. And this length here is OA, and that equals 30. So 30 times 120 equals the radius squared. So this point has been inverted to this point. So whether you're inside the circle, you go to the outside, and if you're outside, you go to the inside, and it's all based on this, these formulas. So that's it. That's circle inversion. Do you want to see what circle inversion can do?
Please.
Right. So I've just drawn a circle within my circle of inversion. So we've only inverted one point. What happens to all the points, the infinite number of points in a circle when you do the same process? Okay.
So
well,
you're going to take that circle and invert it out to...
We're going to invert the circle. That's right. So what do you think is going to happen to all these points? Tell me.
Well, my instinct is that you'll draw another circle out here somewhere, out in the great beyond.
It's going to be circular?
That would be my instinct.
Not an oval?
My instinct is it will be another circle.
Gee, you've got good instincts. So this point here has been inverted to that point there. So you can see the closer it is to the circle of inversion, the closer it is on the other side. So, okay, divide that. Oh, Brady.
What's wrong? Does it go all the way out there?
Yes, we haven't planned this very well. This is huge. So because this one is here, this inverts out all the way to here. So this has already got some very unusual properties, right? Wow, look at this. We've actually gone over the original. Man, we're all over the place with this one. This is huge. So it's different to a reflection where it's not scaled, but this in a sense is scaled. This inverts to this. And what you'll find is that you'll get these points on the edge. You see that? Where they're both touching. There'll be one point where they touch both here and here, and one point where they touch over here and here. Okay? If we measure this length and times it by that length, we'll get 60 squared. Okay? So what happens is a circle will invert to another circle. Okay? And we don't have to do this because we showed before the points go back. So if we started with this circle on the outside, it'd come back to this one. Now the other thing that you need to know is that this is true as well if the circle happens to overlap the circle of inversion. So you could think, oh, what happens if the circle that we're inverting, what happens to this circle, Brady? Will we still get a circle? Well, we will. We definitely still get a circle. This point, if this is A, this will invert to a point there, A dash.
With only a fraction in, like...
Yeah, exactly.
That circle's going to start there, small, and then come out big.
Yep, but what's the 2 points we've already seen on the circle? Can you see 2 points that we already know are going to be on this inverted circle?
The ones that touch the line.
The ones that intersect the line.
Yeah.
Exactly. So can you see there, Brady, we've done a inversion circle, and it's crossed here, kind of. I've cheated a little bit there. But you can see that it still makes another circle. Now, there's one more I've got to show you. Can I just say, it's important that you prove these things to yourself. But I'm not going to prove them today. I'm going to show you this, because this one's weird. And what about a circle that actually passes through the origin? Well, think about it. Well, if there's a point on the origin, right, what's the length from the origin if you're at the origin? 0. So really, it's going to blow up. So points that get very, very close to the origin are going to get huge towards infinity. So we're really talking about a massive circle here. And you know how massive? It just looks like a line. So any circle that passes through the origin of the circle inversion will invert to a line. And lo and behold, check it out. But look at that.
Awesome.
So, circle inversion. Amazing. Look at the properties. Circles invert to circles. Okay? Big goes to small, small goes to big. If a circle crosses the circle of inversion, it still looks like a circle. And then, I think most stunning of all, a circle that passes through the origin will invert to a straight line. So this is all we need. These 2 facts, will kind of fact 1A and 1B, and then fact 2. Okay, that's all we need. So now, with our information about circle inversion, how can we actually solve this problem? Well, what we need to do first, we need to make a decision about what sort of circle we're actually going to use to invert. The way to solve this is to get this bad boy again. And what we're going to do is we're actually going to do a circle of inversion that is exactly the same as our original circle. Okay, so this is our original circle. We're going to put the origin of our circle of inversion right at the end. So this green dotted line is our circle of inversion. And this is what we're going to do all our work with. Okay, so this is our circle of inversion, and remember, it's got exactly the same radius as our original circle. That's important. Now, remember what I said, Brady? What are the things that we need to know about inversions? We need to know circles, invert to circles. If they go over the circle of inversion, they still invert to circles, unless part of the circle goes through the center of origin of the circle of inversion, then it turns into
a straight line.
Bingo. Now, this is the reason why I came. Because now I am able to invert these circles, and just using a ruler, right, I'm able to show you how beautiful, how simple it is now to interpret this problem. This big circle here, Brady, this big circle here, what does it invert to? Well, first of all, it passes through the center of inversion. So we know it's going to turn into
a straight line.
A straight line. Now, where's that straight line going to be? Well, you know what? I don't have to calculate anything, because I already know that it intersects the circle of inversion there. So this is the radius. So this point goes back to itself. So we know that this point is on the straight line, because it intersects the circle of inversion.
I know where the other one is too.
Where?
Over that side.
Exactly. So straight away, you only need 2 points to define a line. Yeah? So that we know we can actually just really simply draw this in. We've just put our first inverted circle. Next, what about this circle here? So this circle here also passes through the centre of origin, but it kisses the inside. It kisses the inside of the inversion circle. Now that means it's going to invert to?
A straight line.
Exactly. But where's it going to be? Is it going to be a straight line like that or like that? Well, let's have a look. This circle here, okay, and this circle here are both going to invert to straight lines, but they only touch at the point of origin. And that point of origin, in effect, is infinity. So, if two lines only touch at infinity, well, this is kind of tricky stuff here.
They must be parallel.
That's the only explanation, really, isn't it? So you see the logic that you can draw out of just these simple rules of circles go to circles. The logic here is that, well, if it goes anything else, it will eventually hit, which means that point must be an intersecting point back here. But we know that doesn't happen because of this origin point. So you can deductively reason what happens here. Okay, Brady, so this big circle is this one, and this circle is this one. Now, what happens to this circle here? Well, again, we don't have to measure anything. This circle here touches the big circle and touches this circle. And we already know that this circle is that line and this circle is that line. So this has to be touching both this and this. And so really, there's only one thing it can be. If a circle inverts to a circle, it has to be a circle that fits between these parallel lines. Well, let's draw that in, Brady. This has happened to there. This point hasn't moved because it's on the circle of inversion, but a circle has inverted to a circle. Now, what about this guy here? How do we invert this one? Well, straight away, we know that 2 points have to be here and here, because they invert, well, they're on the circle of inversion. Where's another point? Well, this one here is on this circle here, and even though it actually, in this diagram, it actually is on an inverted circle, we have to remember that that's not where it's going. It's actually going to here, okay? This guy here, these two touch right there. So this is touching this circle. This circle is this circle. I think you should be able to see what's going on now. If this circle is touching this circle, and this circle, then in the inversion, these two circles are lines, this circle is here. This has to touch that, that, and that, which means it has to be another circle, exactly the same radius, exactly the same diameter. See how much symmetry there is, how beautiful this is, how awesome this is, Brady. I mean, the symmetry of this is just breathtaking. In the inverted world, we still get kissing. Okay. Now, Brady, there's another circle, this blue one here. This is the guy here, which is 1/15 of the original radius. This is what I told you. Now we actually have to invert this guy. So this circle is that circle. This circle is that circle. This circle is actually over here. So that circle's there. So this guy in here is kissing 1, 2, 3. And of these purples, it's 1, 2, 3. So we know that this blue guy has to actually be in here. Has to touch all three.
So is it a rule that if you kiss in real life, you have to kiss in the inversion too?
Exactly. Now this little circle is the inversion of the blue circle. What about the one that we really want? This one down here. How do we get there? Well, we've inverted 1, 2. We've got to invert this guy now. So this guy inverts. And you know what? It's becoming so simple to do because we know that it's a circle that has to touch this guy here. So this is touching this. And this is this. So this circle has to touch here. It's touching the big circle, which we know is that line. We know it's touching this circle, it's that line. So it's just a straightforward process where we now have to just draw circles in, one on top of another. This Pappus chain of circles, getting progressively smaller and smaller and smaller, under inversion ends up being circles stacked on top of each other, exactly the same radius, exactly the same diameter, because they're fitting between two parallel lines. So this is absolutely beautiful. This is this one, this is this one, this is this one, this is this one, this is this one. So now if we think about it, in the Pappus chain, the blue guys are touching these circles and touching this circle here. So in the inversion, okay, we've already seen that this blue circle inverts here, so the pattern is going to stay the same. There's going to be a circle there, 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 and they're all going to be exactly the same size. Okay, so if we can work out the diameter of this, we can work out the diameter of this, and then we've got the radius. So how can we do that? This is epic. This is seriously epic. All right, here we go. So we've got, now this is a right angle, and we know that this circle here, even though that's so tiny, the center of this circle will pass through the center of this circle up here. We now have a massive right angle triangle. If we know this length here, we can invert that length and it will give us the length through this circle, and because it's passing through the origin of this little circle, it will tell us the diameter, and if we divide that by 2, it'll tell us the radius. So shall we do it? Let's bring this home. I tell you what, this is absolutely epic. It's very pretty though, isn't it? This whole length here is R. It's the circle of inversion. So this half here is going to be R on 2, right? And this length here, well, this circle here is a half of that. So right from here to here, that's R on 4. And this little blue inverted circle here is a quarter of that there. So that's actually R on 16. So just here. So what we're going to do is, we know that this whole length here, all the way across, R take R on 16, which is equal to 15 R on 16. So that's what that length is equal to. Now, what about this long guy here? Well, again, here, this distance from here to here is going to be, that's R on 4. And all of these are R on 2. R on 2 plus R on 2 plus R on 2 plus R on 2. So that's going to be R plus R, so that's 2R plus R on 4. So what we've got here then, so this whole length here, wow, that's huge. 9R on 4. Now what we want to do is, now that we've got Pythagoras' theorem, and we worked out this length and this length, we can work out the hypotenuse from this O, which is the center of the circle inversion, all the way to this center here of this blue circle. When you work that out, that comes to 39 on 16R. Now, we actually want to know the distance O to B dashed, because we know that will invert right back to this small circle. And we also want to know O to O dash. But let's do this one first. So we know that O to B dash is equal to 39 on 16R plus the radius of the small circle, which is R on 16. So that equals this. OA, so OA's over here. We're going back from this by R on 16. We're going back by the radius. So it looks like this, 39 on 16R take R on 16. Same denominators, so 39. So we end up getting 38 on 16R. Now, we want to invert these. So we want to take O to B dash back to B. Okay, so let's do that. So O to B, when we invert this, we end up getting 16 on 40 R. Okay, and we do the same thing with O to A dash. We bring it back to the tiny little circle there, and that means O to the A is this inverted. Okay, and then we end up getting 8 on 19 R. Now, we've got O to the A, O to the B. We know they passes through the center. So we know if we go OA take OB, we will get the diameter of this small circle. And that happens to make it 2. So that's that, take that, which ends up being 2 on 95 R. And because the radius is half the diameter, so the radius here of this small circle, so radius of small circle equals 1 on 95 R. So we know that the original circle, if we divide by 95, will give us that radius, which means this is 1 on 95.